So we've had a lot of great presentations today. I'm going to start off with my own version of light technology humor. I think there's been a lot of great discussion today about this kind of ground-changing event we're going through, the adoption of cloud and SDN technology into the telco space, right? I view it more as physics and economic physics than of anything of faith. It's really unavoidable, right? We have the pressures of the Googles of the world who are continuously being able to rapidly launch services, rapidly prototype new offerings, develop things quickly. And we've put our service providers in this space where they've got tons of equipment. And what you can barely see there is the old buggy whip, now gone from our minds. Nobody probably has one in their house, or if you do, you must be pretty strange. But all of these things are the next buggy whip, right? The operators are completely tired of dealing with proprietary hardware platforms that have individual sparing systems, purchasing spares for every different type of product that we bring them. And my company has done this role for many years, right? What has changed? Well, what has really changed is the maturation of cloud and SDN technology combined within the telco space, the emergence of all IP communications, right? In the old days of TDM and tip and ring, we could have never considered bringing those communication interfaces into a cloud environment. But with an all IP-based communications infrastructure, you can leverage these new software paradigms to solve this problem. The other problems that equipment creates for an operator is space, right? Every time you rack and stack one of these things into a network rack, it requires a different amount of physical space than the previous piece of equipment that was there, different types of network cabling, custom switching and routing, very complex, specialized skills to bring each unique piece in. Could be IMS core assets, session border controllers, application servers, EPC core elements. All very, very, very different from every vendor, and every vendor's product, even within the same space, is very different, right? Creates a nightmare for the operator every time they bring that system into their network. Capital investment is huge, right? Every time they bring this new network asset into their network, they have to go through a CapEx and OpEx nightmare that takes in the order of 12 to 18 months to bring and deploy the next service into their network. End of life is painful. They end up flushing all this equipment and depreciating it. The end result is this cycle that the operator's gone through for many, many years takes a long time, from procurement, RFPs, RFXs, through to design and network design changes, integrating that into the network, fully testing it, going through system test cycles, and then deploying it as a service. From idea to running service can easily be 2 years, right? What's this doing for them? It's put them in a position where the rest of the world moving to IP and software-based infrastructure can move very, very quickly to enable new service revenues. The operator cannot, right? And NFV, cloud and SDN technologies are critical to changing this dynamic for them, so they can really enable new revenue streams. It's also constraining innovation. One of the things that you'll see that cloud and SDN, NFV technology can do for the operator is the ability to prototype new services and deploy them quickly on a production environment that's actually being used to deploy live traffic. Test it quickly, turn it up dynamically, destroy it, or launch it into service. Much, much more rapidly, enabling lots of startups and smaller proof of concepts to come into their labs and be tested for deployment without having to qualify any hardware or equipment to do it. So we've had a couple of great sessions up here. I was dying to present this slide because I have kind of a tweak to the way that this is usually presented, trying to explain how these different technology areas overlap. These two technologies, cloud and SDN, would exist for quite some time without us ever creating NFV, right? These are different. They overlap a bit. Cloud gives us compute abstraction, right? The ability to dynamically allocate compute resources in a data center architecture. To automate metal management, we constantly look at cloud and virtual machine architectures with forgetting or trying to abstract ourselves away from the physical hardware they run on, but in the end, they do run on hardware. There is metal in there, but it's managed via the cloud infrastructure. Dynamic resource configuration, right? The ability to dynamically create and spawn instances within that environment. SDN is also useful, right, for a different function. It's for networking abstraction, software-controlled network infrastructure, right? As you dynamically spawn some new VM into your data center, it appears on what appears to you perhaps a random server as it is brought up. There is both intra-cloud and extra-cloud SDN configuration that's required to dynamically bring that thing into service. Now, what happens with NFV, right? In the web and cloud environment that we've been in for some time, there's really no standards activity going on here. And some would say that's a really good thing. It moves things forward very quickly. However, all those cloud infrastructures, whether we talk about OpenStack, VMware, Eucalyptus, Joint, whatever, they're all different. They all have different APIs. I, as a software vendor, looking to deploy an elastic service into one of those cloud environments, have to build it uniquely for each of those infrastructures, even if I'm on the same hypervisor, right? And that's because their methods and APIs for scaling and for dealing with redundant failover and metal management are all different, right? What NFV does for us is brings a communication specificity to the use of cloud and SDN, right? Taking the best of elasticity and orchestration from cloud and automation and network isolation that you get from SDN and applying the communications infrastructure to it in a standards-based way. By applying standards there, if ETSI NFV is successful as we go forward here, those standardized APIs could conceivably allow me to launch my application and not really care whether it's on Eucalyptus, Amazon EC2, Rackspace, OpenStack, or on a private cloud running Eucalyptus, right? Because I'll be using the NFV APIs through the NFV orchestrator and managers to request the instantiation of a new VM for one of my VNFs. So we have a lot of hope here, right? This is a really great standards activity that's going on. In the interim, we're getting a lot of pressure. As some of the others have mentioned up here today, RFPs are flying in. There are proof of concept and demos going on. We have to execute, even though NFV is running in parallel. So what you'll see today, in particular, is a couple architecture examples of how we do this on OpenStack. Much of the philosophical goals of NFV, that being elasticity, orchestration, automation, right? They're all possible today on any cloud infrastructure. They're just not in a standardized manner. So we can achieve for the operator what they're looking for while NFV standards continue to mature. In other words, we're not waiting, we're implementing, right? In order to have NFV be successful, you really have to have a significant number of the network functions that we look at today move into this new space. If I take a single product, like just an SBC or just an app server, and put it in the cloud, that's not sufficient to justify the build of an entire data center, right? The economics of scale and the reduction of CapEx and OpEx come from multiple applications coexisting within that infrastructure. So NFV's philosophical goal is everything. Everything that we can possibly fit into this data center architecture, the more and more virtual network functions we turn them into, the greater and greater the return on investment you get from this type of approach. Effectively taking all these communications applications and moving them to standard data center architecture, utilizing OpenFlow for SDN, OpenStack and equivalents for the compute, and highly scalable database such as MongoDB, Cinder, and Swift for the storage infrastructure enables us to enter the data center environment with all of our communications applications. So the real title of this presentation from us today here is Embracing the Tenets of Cloud and SDN, right? As you can tell, NFV really can't exist without Cloud and SDN. Cloud and SDN can exist without NFV, right? And will continue to. But NFV is critically dependent upon them. And in order to make NFV really successful, we have to embrace elasticity and some of the more advanced tenets of these technologies. This is where the economies of scale and the CapEx and OpEx reductions come from. At this high-level block diagram that we have here, on the left side of this slide, we have physical network functions that you would deploy as if they were in appliances today. ATCA racks, physical proprietary systems, right? They have compute resources, and there's a lot of software running on them today, right? You build them. But a lot of times, especially if you're not at peak busy hour for voice applications, for example, there's a lot of idle resources in each one of these network functions, right? However, those idle resources are not fungible across these other applications. An SBC can't use an application server's compute horsepower, right? These are physically isolated systems. What do you have then as a result? Especially for a large operator, which has a large geographical footprint, You may have peak busy hour in one region of your geography different than another. And yet it's the same resource. It's busy in one location, not busy in the other, right? So by moving these things to virtual network functions in a fungible resource pool or a general purpose compute cloud architecture, these things can scale independently, and in aggregate, the operator can buy less, right? They can buy less compute resources than what was represented by the physical platforms that they had before, right? And in moving to this, lower CapEx, lower OpEx, especially OpEx with regard to the specialized teams that run this type of infrastructure. It now becomes more of an IT data center. You still have the specialized expertise that goes with IMS, that goes with app servers and SBCs and SIP and all that. It's probably a good point to mention that I think one of the reasons why NFV and cloud is being adopted so rapidly into the operator environment, it's not the next IMS. Don't confuse it as an IMS. It's not a re-architecture of communication systems. NGN or IMS architectures, video and audio interworking, bearer path handling, EPC, edge RAN equipment, these functions can all exist in today's architectures on this new infrastructure, right? It's just a matter of what it's physically running on, proprietary systems or general purpose compute and cloud, right? The things that we're adding here, software-defined networking and elasticity and orchestration, are key to generate the maximum benefit from moving to this environment. Simple example, right? Here's two network functions. At time 0 and 1, they may have different minimum and maximum horsepower use cases, right? This requires a significant amount of physical assets deployed to handle that. Even though this application here is idle, it may have to scale up to this peak resource utilization, right? Same here. He runs at a different idle pace and maybe needs to scale higher. What I can do at time 0, instead, by going to a cloud environment, I can have this common pool of resources where this application is only using 2 instances, and this is using 7 or 8, whatever that is, and they're dynamically sharing that. As the network load increases on this red application, the blue application scales back, right? This is easily realizable through different applications intermingled on the same cloud, as well as through different peak busy hours. So that's really how the give and take and releasing of virtual machine assets and the pulling in of virtual machine assets happens dynamically. When you multiply this across hundreds of instances in a cloud environment, the economies of scale are incredibly compelling. Another argument for elasticity and adoption of it wholesale is really the end goal, the target nirvana, if you will, of what you can do once you've implemented functions under this architecture. No longer are we thinking simply of dynamically scaling within one data center. We can dynamically scale across network load, immune to geographical boundaries. Before, if you had to spin up an instance in a different geographical POP, you were rolling a truck, racking a system, turning up a network, and then having idle resources during idle periods. Now you can dynamically spawn a network instance in a remote data center. You can physically separate signaling and bearer path assets and have them scale independently in different physical locations. You can move licensing dynamically from one point in your network to another and tear down a bearer path access element and turn it up somewhere else, right? The real advantages of elasticity go beyond CapEx and OpEx to create an architecture that is maximally flexible for the operator, enabling them to move their assets around in the network dynamically and then use SDN to bolt up the networking paths to deliver traffic to those functions as they run around. Automated orchestration, can't say enough about that as well. Orchestration is a little different than elasticity, right? Orchestration of multiple VNFs, as well as the VNFs themselves, is a key aspect of this. As we own virtual machine environments with multiple or many high count of instantiations, an orchestration method is necessary to manage all that infrastructure. Tying that into the NFV orchestrator so that we have control over this infrastructure and can deliver SLAs to our customers, the service providers, is critical. A word on another great question that came up earlier today. Talk about the difference between virtualization and cloud. Very big thing. It is really not sufficient to take what used to be a physical appliance with its software running on it, even if it was a server, and just virtualize it. After what we've just talked about, you can see that elasticity and orchestration are key architectural tenets of being successful in this new architecture. So don't just virtualize your application. change its architecture so it can scale properly. Often this means that you end up creating a tiered architecture with load balancers and IP sprayers at the front end, with horizontally scaling application tiers in the center that dynamically expand and contract to absorb dynamic workload from the network. And then often you'll see independent horizontally scalable databases like CouchDB or MongoDB, which are typically associated more with contemporary web applications being used in these communications environments. You know, in a lot of our applications, we've moved from SQL architectures to NoSQL architectures to make the maximum benefit to this. Some of these database architectures are incredibly compelling. The ability to have ghost backups that you can pull from for analytics processing without impacting the live application. Sharding databases across multiple instances to increase compute horsepower. The ability for the application to scale effectively then needs to be matched by load balancer and IP sprayer layers scaling and database scaling, as well as EMS and cloud management, right? You can't just scale the applications. The entities that feed it work, you know, if this were an SBC and we're feeding SIP signaling into this, this could be a choke point, right? This has to have its own scaling capability. The database could max out if it was only a single SQL instance. By going to a horizontally scalable database, it can scale with the application. The whole thing has to grow and shrink almost as if it were a living organism as the workload is applied to it. That's squeaky. So let's talk a little bit about orchestration and management. We'll start to tunnel deeper into the OpenStack architecture here at a very high level. Orchestration is really an independent function that sits outside the virtual network function itself. It's important for these applications to scale up and down dynamically. And you really need an independent application looking at these VNFs, looking at their performance criteria, looking at CPU utilization, memory utilization, concurrent session count, whatever your metrics are for your particular VNF function, that's going to demand that you detect, I need to scale up or I can scale back, right? So the orchestrator tends to watch that. The NFV manager and orchestrators watch your applications running, gather statistics from them, and make dynamic changes to those applications. How are those dynamic changes made? Well, today, as we talked about earlier, we will use direct calls into OpenStack APIs. In the future, we see this being VNF APIs, right? Or NFV APIs, I should say. So whether we're using metal management and orchestration calls into Mass or Puppet in this case, Nova, which is the scalable compute management system in OpenStack, is the entity you go to ask for a VM to be dynamically spun up. Glance is the image repository. Neutron for intra-cloud SDN calls. OpenFlow or to external Open Daylight type infrastructures to make SDN manipulations of the live network equipment. Dynamically and statefully working through these APIs to cause the change that you want in your application tier to happen is how you effectively implement elasticity and orchestration. So if I need a scale instance to go up, I'll make calls into Glance to pull the image. I'll make calls into Nova to dynamically instantiate the scale. I'll make calls into Neutron to dynamically set up the networking within the cloud. Right? So it's very important to work with these open standard APIs, especially as they evolve through the NFV initiative, to implement the architecture. How important is SDN to NFV? Well, I think it's absolutely critical. To date, the standards activity has really looked towards the virtualization aspect and the automation and orchestration, which is a great place to focus. But in reality, I think it will only be successful once SDN is fully adopted. There's really two types of SDN I'd like to talk about today: intra-cloud SDN and extra-cloud SDN. Separating these into two kind of buckets lets you think about them independently. Intra-cloud SDN is as you dynamically create VMs, and these are physical compute nodes in the network. This is an open vSwitch architecture in the Grizzly release of OpenStack, which has since been replaced in Havana. But as these things are dynamically created, you can set up virtual networks within the infrastructure of the cloud so that you can get these services running on their own dedicated network architectures. Some functions like a TAS, for example, might have an ISC interface into an IMS core. It may have diameter billing interfaces into a billing mediation system. OSS, BSS infrastructure, diameter to the HSS. All of those are network paths that need to be dynamically set up in this environment. Calls into Neutron API allow you to set these things up. So depending on whether I'm instantiating a TAS or an SBC that may have private and public side interfaces and denial of service protection and flow control needs that you have that are different than a TAS, which is a different network function, you use calls into Neutron within this cloud environment to set it up on the right physical and logical networks. In many cases, you may have a dedicated redundant LAN, switch to LAN, layer 2 LAN for the database, for the management infrastructure, and for specific networks that are connected to the compute nodes in the cloud. The design of your cloud networking is critical and is tied to the service you're going to launch. For example, in the SBC case, I may want multiple physical networks to create physical isolation between the public and private side of that system, right? For high-scaled M+1 or active-active architectures where I've got a lot of database queries running out of these VMs, I may want a dedicated database LAN, right? Choosing the architecture, the physical architecture of the cloud infrastructure, and then using the SDN layer to control it is a key part of launching these dynamic services in the cloud. That lets us create a logical equivalent, right? We move from this physical picture we had in the previous slide to really what we're controlling now is a logical visualization of the virtual networks that we've created within the cloud environment. So that each of these instances where the cloud infrastructure may have dynamically allocated these VMs onto physically different machines, right, shouldn't really be visible to you, nor should you care about it. Logically, you need to be able to bring those networks into the controlled architecture that you need to put them in order for them to function properly. The isolation of walled garden networks versus access and interconnect networks, right? You've got to be able to separate them. And then finally, we'll move in the next slide to Extra-Cloud SDN where we start talking to the external routed infrastructure, right? So we've got to control hypervisor switching, Open vSwitch, and ML2 infrastructure in the case of OpenStack for the Intra-Cloud SDN. This philosophy that you see here in this bullet, automate everything, is one of the most core tenets of cloud infrastructure. Taking a virtualized application and putting it in a cloud and telling an operator they've got to go in and manually scale the thing up and manually change the networking is a non-starter, right? We've got to use the automated software architecture and our knowledge of our applications so that this thing scales automatically under software control. Let's see here. And then it's worth noting, right? This is just a small list, right? But the types of network architectures and physical network interfaces that used to be done physically in the network, you go into the NOC or the central office and see physically separate networks for bare plane access, interconnect, signaling management, OSS, BSS infrastructure and provisioning. These now need to be done logically, but with knowledge of the infrastructure we're running on, so the same goals are achieved. You can't implement a virtual networking design that ends up having traffic overflow on one type of interface breaking another one. The fundamental tenets of what we did in the appliance environment still apply in the cloud. So you've got to use your knowledge of the cloud and the SDN infrastructure to implement the same functions and have them work properly in this environment. Extra-Cloud SDN, right? So once we're coming out of the cloud, right? Going through SDN controllers via northbound interfaces and talking through OpenFlow into individual nodes is critical, right? Whether it be interworking with the core and aggregation and access topologies, right? Dealing with the intra-cloud switching equipment at top of rack, end of row, controlling layer 2 and 3 routing externally, and doing software and hybrid control, hybrid being external and internal pre- and post-cloud environments, is really critical. So in addition to the intra-cloud infrastructure that we were controlling and manipulating to make the virtual network function work, we now go to external equipment to control that as well. Particularly critical as we bring media and Bearpath into the cloud. Metal as a service. Metal as a service exists in every cloud infrastructure. And certainly the NFV vision is to have all this virtualization work on any of these, right? I should be able to, as an operator, choose based on my own decision which one of these I want to use and deploy my services on it, right? Keep in mind, though, that one portion of the cloud architecture is metal control, right? Metal management, where As you decommission a server or add new servers to the data center, those things are dynamically added back into the cloud management system so that Nova, for example, can allocate VMs onto a larger count of servers, right? It is an option to use this infrastructure, Metal as a Service, Crowbar and Dell or VMware, to dynamically control and request specific assets for your applications to be deployed on. That's of particular interest for bearer path applications. Another huge benefit, I can't emphasize this enough, when designing products to be VNFs, virtualize everything. Virtualize the entire test infrastructure, okay? The benefits of a virtualized application don't stop at the operator. They also work for the developer and product generator, right? Such as the equipment vendors as ourselves, right? By taking a virtual unit under test, this particular horizontally scaled application, wrapping it with an automated virtual test harness, right? So that you can run this in the cloud from test 0 to test 1,000,000, right, to completion. Then allows me to spawn them in a hyperscale environment, such as Rackspace, Amazon EC2, your own cloud environment, right? And run the tests with a hyperscale parallel automation framework. What does this let me do? Previously, one of the problems that causes us to be incredibly slow to market in the telecom domain is spending 12, 18, 20 weeks in system tests, testing every possible use case of a product. How about being able to break that down and run it massively in parallel? Get to higher percentage levels of test coverage and do it fully virtualized in a fraction of the time, right? From a cost standpoint, turn these things up in the cloud, run them to completion, and tear them down again, right? Dynamically orchestrate those resources as part of your test functionality. By adopting virtualization from kind of birth to cradle to grave, right, you get every aspect of product development gets touched in some way to the benefit of the customer for a higher quality product and to your benefit and faster time to market. Finally, a word on transition, right? The world's not going to go from this appliance monolithic world they're in today and jump directly into geo-distributed hybrid clouds, right, with overflow into public clouds. They're going to need to go there stepwise. So across our portfolio, we're doing a lot of things to ensure physical assets can be shared by cloud environments as we go in a hybrid cloud environment, but not hybrid private-public, hybrid from appliance to post-cloud, right? And in this way, we can move the operator gently at their own desired transition pace, perhaps, for example, having media assets externally while signaling controller in the cloud, and then eventually moving media into the cloud, right? And then going to more advanced architectures like geo-distributed. So having a stepwise evolutionary path to enable them not to have stranded assets in the physical appliances they bought, but have them interwork with the cloud is critical to succeeding in this market. And then, this is kind of the wrap-up, right? The emphasis I've tried to create here is on fully embracing this technology. Don't just virtualize your application, right? Embrace elasticity, orchestration, automation. Fully embrace SDN and leverage it, right? Automate your test environments. Use all the capabilities of the cloud, even Metal as a Service, right? And enable a hybrid cloud environment for your customers. By adopting this type of an approach, you can be very, very successful with the products that we build, and the operators will be most pleased with what we deliver them. At Genband, this is what we're doing. We're doing it across our entire portfolio. I guess what we'd say, much like Alcatel-Lucent today, and you heard Metaswitch, we're all in, right? This is physics. This is destiny. There's no doubt in my mind, after spending significant time in this market, that this is where we're headed, right? 2014, I think, will probably be the year of proof of concept and early deployment, with 2015 being the rubber hits the road. But we've really got to execute against this, because inevitably, if you're not selling this a few years from now, you won't be selling product.